Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to write nuclear equations for a variety of different types of decays: beta decay, positron emission, electron capture, and yes, again, alpha decay. So let's get into this. So for the first one, we're asked to write the equation for the beta decay in berkelium 249. So BK 249. So once again, they're telling us it's beta decay. So we're going to start with BK 249. We're going to write that isotope symbol. So we have BK, and the 249 is the mass number. So we're going to put that up here, 249. And then the atomic number, we look on the periodic table, and the atomic number is 97. So we're going to put 97 down here. And of course, the decay is a beta decay. A beta particle is an electron, so it's going to have a negative charge, zero mass. So it's going to be some sort of isotope, daughter isotope, plus the beta particle, which is represented as an E with a -1 on the bottom and 0 on top. It could also be a beta symbol, right? So we could instead of having the E, we could just write the Greek symbol for beta and do it that way. It would be the same thing. So here we have our beta particle. And so again, we need to figure out what our daughter isotope is. So again, we need to balance the sides. So the total on this side has to equal the total on this side, top and bottom. So I have 249 total on this side, and I have 0 plus something is going to give me 249. If I subtract 0 from 249, I get 249. So that's going to be 249 on top here. And then here on the bottom, I have 97. If I have a -1 here and then something here, this plus this gives me 97. If I subtract a negative, then that's like adding a positive. So it's like adding one. So subtracting -1 is like adding 1. So that would be 98. So 98 minus 1 gives me 97. So this would be the nuclear equation for the beta decay of BK 249. Now, what about positron emission of oxygen 15? So once again, we need to write oxygen 15 as with its symbol, its isotope symbol. So we're going to have oxygen, and the mass number is 15. So that's going to go on top. And we look on the periodic table for the atomic number, we get 8. So it's got 8 down here. So this is going to undergo positron emission. Positron emission means it's going to be emitting as a product. So this is going to be a product. So we're going to get some sort of isotope plus the product, which is a positron. A positron is seen as a positive electron. So it'll have the same numbers here, except instead of a -1, it's going to be a +1. So this time I'm going to write it as an E. It's like a positive electron. So it's going to have a +1 on the bottom and again 0 on top. So it's like a positive electron. So now that I have the positron written as a product, now I can figure out what the numbers here for this isotope are. So I have 0 on top over here plus whatever this is should give me 15. If I subtract 0 from 15, I get 15. So 15 is the number over here. So 15 plus 0 gives me 15. And then I have a +1 here. 1 plus something gives me 8. If I subtract a +1 from 8, that gives me 7. So 7 plus 1 gives me 8. And so now I have the nuclear equation for the positron emission of oxygen 15. Next, we have the electron capture in iodine 111. So first we want to write down iodine 111 as the isotope symbol for that. So we're going to have I, and then 111 is its mass number, so that goes on top. And if we look on the periodic table for the atomic number of iodine, that is 53. So we're going to put 53 down there. And this is undergoing electron capture. So as the name capture indicates, this is going to be taken up by the iodine. So this is going to be a reactant. So we're going to add the electron to this side. It's capturing electron. So we're going to take the electron here, and it's going to be 0 on top, -1 on the bottom. So we add those together, and we want to produce something. So again, we're going to have a new daughter isotope on this side. And so here, again, we're balancing the total top numbers and bottom numbers. So 111 plus 0 gives me 111. So we have a mass number of 111 on top. And then here, oops, I forgot to identify what these elements are. So this one's 98. So we look on the periodic table for 98, and that is californium. So CF, sorry about that. CF. And then this one, this has a 7. So we look up the atomic number for 7 on the periodic table, and that's nitrogen. So this one is nitrogen because of the atomic number 7. And finally, we're back to C. So we've already balanced the top numbers. 111 plus 0 equals 111. 53 minus 1 is going to be 52 on this side here. So now I have the bottom number, which is the atomic number. I look up number 52 on the periodic table, and I get Te. So we're going to erase this, put the symbol Te for that isotope. Okay, last but not least, now in this case, they're asking us to write a sequence of steps. So here we're given, and we want to write down the nuclear decay sequence of uranium-235. And first it's going to undergo an alpha decay, then it's going to undergo a beta decay, and then another alpha decay. This is called a decay series. So we start as we usually do. Uranium-235, we write that as the isotope symbol. So here we're going to have U-235 is on top. And the atomic number for uranium is 92. So we're going to put 92 on the bottom. So we're told it undergoes an alpha decay first. So we know that's going to produce an alpha particle. So we're going to put some sort of, it's going to produce a daughter isotope plus the alpha particle. The alpha particle is a helium nucleus. So that's going to be 4 on the bottom, 2 on top. So again, we want to balance this. So 4 plus what gives me 234? That's going to be 230, right? 230 plus 4 gives me 234. And then 2 plus what gives me 92? That's going to be 90. So 2 plus 90 gives me 92. Okay, so here's the alpha decay. Now, we got to figure out what element this is. If we look up 90 on the periodic table, we get thorium. So we're going to erase this, and we're going to put TH. Let me write that better. So that's going to be TH. Okay, so now we have a new daughter isotope. Now we're told that the next step is a beta decay. So that means that our new daughter isotope is now going to be the next parent isotope, and it's going to undergo a beta decay. So we do that by then taking the thorium here, the thorium-230, and we write it as the next step, thorium, and then here we have, here I'll write it over. So here we have thorium-230 and 90 on the bottom. And now this is going to undergo a beta decay. Remember, a beta particle is an electron. So it's going to undergo, it's going to release or give off an electron or beta particle. So that means that it's going to produce another daughter isotope plus the beta particle, which is an electron. So now I just need to balance the numbers on both sides. So 230 on this side, 0 plus what gives me 230? Well, 230. So stays 230 on top. And then 90 on this side, -1 plus what gives me 90? Well, that's going to be 91. And then I look up 91 on the periodic table, and it turns out that that's Pa, the symbol Pa. I think that's proactinium, not Pennsylvania. Okay, so now I've undergone the beta decay, and so my new daughter isotope is here. The next step is, I'm told that that new daughter isotope, the next step is an alpha decay. So now the new daughter isotope becomes the next parent isotope, and I'm going to write that down here. So we have Pa, so Pa there, and then we have 230 on top and 91 on the bottom, and that's going to undergo an alpha decay. So it's going to release an alpha particle, which is the helium nucleus. So we're going to get some daughter isotope plus helium. So 4 on top, 2 on the bottom. And finally, we balance the numbers. So 230 on this side, 4 plus what gives me 230? That's going to be, if I subtract 4 from 230, that gives me 226. So I have 226 on top. 226 plus 4 gives me 230. And then 91 on this side, 2 plus what gives me 91? That's going to be, if I subtract 2 from 91, that gives me 89. So I have 89 plus 2 gives me 91. Now I know 89 is the atomic number. I look up 89 on the periodic table, and I get actinium, AC. And that, ladies and gentlemen, is how it's done. This is how you write out your nuclear equations for various types of reactions, different nuclear decays. So I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please like the video, share the video, hit that like button, and also make sure you subscribe to my channel. Hit that notification bell, and when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.